Hey math students, in this video we're going to go over partial fraction decomposition. In algebra, usually we're concerned with taking two fractions and getting a common denominator so that we can combine them. However, in calculus there are many problems when it's easier to work with a large fraction if we break it up into multiple fractions. Partial fraction decomposition is the process through which we break up a large fraction or decompose it into multiple parts. Before we go on to partial fraction decomposition, let's have a quick reminder about how we would combine two fractions with uncommon denominators. So say we wanted to carry out this subtraction. We would take this denominator, x plus 1, and multiply it on top and bottom by the first fraction, and then we would take this denominator, x minus 3, and multiply it top and bottom by that fraction. Now we can carry out the multiplication for the numerators and rewrite this again in terms of two fractions. So that first one is not a 2, but it's 3x plus 3 all over x plus 1, x minus 3, minus 2x minus 6 all over x plus 1, x minus 3. Now we see that they have a common denominator, so we can combine them. So we get 3x plus 3 minus, and I'm going to put parentheses here, 2x minus 6, because we need to remember to distribute this negative to both terms, all over x plus 1 times x plus 3, and that should be a minus. So now we are here, and to finish this up, we just distribute that negative through. We get 3x plus 3 minus 2x plus 6 all over x plus 1 times x minus 3. And then that all equals 3x minus 2x, which is just a single x, and a positive 3 plus a 6 plus 9 all over x plus 1 times x minus 3. When asked to find the partial fraction decomposition, we will reverse the order of finding common denominators and combining two fractions. In order for you to see how this correlates, we will find the PFD of the example we just walked through. So we begin by noting that the denominator has been factored into two unique factors. This means that this fraction will decompose into two fractions. The first one is going to have the denominator x plus 1, and the second will have the denominator x minus 3. And we want to set these equal to each other, so we want to find an a and a b that make this equality true. We start by finding a common denominator on this side. We take our x minus 3, multiply it on top and bottom to this side, and we take our x plus 1 and multiply that on top and bottom to this side, and carrying that multiplication out, we get ax minus 3a plus bx plus b all over x minus 3 times x plus 1. And since we didn't touch the left side, that stays the same. X plus 9 over x plus 1 times x minus 3. Now if we want these two fractions to be equal to each other, we note that since the denominators are equal, this will be equal if the numerators match. So now we're going to forget the denominators because we just want the numerators to match up. We've got x plus 9 equals ax, and I'm going to go ahead and group like terms. So we have an ax and we have a bx. So I'm going to say ax plus bx, and then minus 3a plus b. Now this is the fun part about partial fraction decomposition. We see over here we only have one x. So we are concerned with the coefficient for x on this side. Since we have an ax plus b, we can factor the x out of both of those and say a plus b x is equal to ax plus b. And so now we keep this other part the same, minus 3a plus b, and still that is equal to our x plus 9. Now we look at the number of x's on each side. As we said, this side only has one x, and this one has an a plus bx. In order for those to be equal, a plus b needs to equal 1. And then we look at the constant. We have a 9 over here, and these two terms are both lacking an x, so we can say that negative 3a plus b equals 9. And we can now solve this system for a and b and find out what they are and plug them back in where we started. So let's go ahead and solve this system by substitution. If we solve for b here, we get b equals 1 minus a. We can now take that b and plug it into this value. So this becomes negative 3a plus 1 minus a equals 9. We have negative 3a minus a gives us negative 4a, and then we have a plus 1. If we subtract that to the other side, we get equals 8. And now, dividing both sides by negative 4, we have a equals negative 2. With a equaling negative 2, we can solve for b. b equals 1 minus a negative 2. That comes from this equation right here. So b equals 1 minus a negative, so plus 2 equals 3. So we now have solved for a and b to make our initial equality true. So we simply come back up here and we will get rid of these and we'll replace our letters. So that was a, so a negative 2 goes there. And then b is equal to 3. So we change b to 3, and we have just successfully decomposed this fraction into the combination of these two fractions. Now pause the video and see if you can find the partial fraction decomposition of this fraction on your own. Alright, we'll now go through very quickly how to solve this one. First, we notice that the denominator is factored into two unique factors. So we set it equal to this. We find common denominators. Get ax minus 2a plus bx plus b all over x minus 2, x plus 1. That's all set equal 5x minus 1 over x plus 1, x minus 2. Since the denominators match, we set the numerators equal to each other. And I'm going to go ahead and group like terms. Ax plus bx minus 2a plus b. So our a plus bx minus 2a plus b. For this equality to hold, a plus b must equal 5. And negative 2a plus b needs to equal a negative 1. Solving this, we get b equals 5 minus a. Plugging b into this equation, we get negative 2a plus 5 minus a equals negative 1. negative 2a minus another a is negative 3a, and subtracting 5 over, we get negative 6. A is therefore equal to 2, and then b is equal to 5 minus 2, coming from this equation right here, which is in fact 3. So a equals 2, b equals 3. We come back up here, get rid of the work we did to find common denominators, and we simply replace a and b with what we solved them to become. And this one equals 3. So, if you got that, you are right. Throw yourself a pizza party with some nachos on the side. And if you didn't get it, keep on keeping on. I know you can do it. Now that we've spent time with the first case of a partial fraction decomposition, let's go over some rules and things to consider for any other case we might encounter. The first thing we need to make sure of is that the numerator is less of a degree than the denominator. So for this case, we have an x cubed over an x squared. We would need to do either long or synthetic division and then do partial fraction decomposition on what's left over. We also need to make sure that the denominator is in factored form. If, for example, we were given this fraction and asked to decompose it, we would need to factor the denominator before we can move on with that. Once it's in factored form, the number of unique factors is equal to the number of fractions in the PFD. Also, if we have more than one factor, then it's going to be set equal to every degree of this factor. So negative 5x over x minus 3 cubed will be set equal to a over x minus 3 to the first, plus b over x minus 3 squared, plus c over x minus 3 cubed. And finally, if one of the unique factors is nonlinear, then the top part of that decomposition will be 1 degree less. For example, one of the factors in this fraction is an x squared minus 3x plus 7. So that gets set equal to a linear function, ax plus b over that unique factor. And we can see the other one's just a simple x plus 1, a linear factor. So that's just the normal b over x plus 1 that we've seen already. So now let's talk. If you were asked to find the partial fraction decomposition of this fraction, how many fractions would this decompose into? The answer is there would be possibly 7 fractions. It's because it would be equal to a over x plus b over x squared, and that covers that factor, plus c over x minus 1 cubed, plus d x minus 1 squared, plus e x minus 1 cubed, plus, now remember this is nonlinear, so it's going to be fx plus g over x squared minus x plus 1 plus hx plus I over x squared minus x plus 1 squared. 1, 2, 3, 4, 5, 6, 7 fractions. All right, let's walk through another example. Let's say you're asked to find the partial decomposition of this fraction. How many individual parts is this going to break up into? If you said 3, you're right. Let's go through it and see what it looks like. And I'll apologize now, it's a pretty big problem. I might have to write a little squished so we can fit it all. But it's going to equal a over the first factor plus b over the second factor to the first power plus c over the second factor squared. So now we want to combine these three fractions to get them to look like that. In order to get a common denominator, our goal is x minus 1 times x plus 3 squared. So all that's lacking here is our x plus 3 squared, x plus 3 squared. If we have an x plus 3 already, we're going to want to multiply by another x plus 3 and an x minus 1. So that's what we're going to do on top as well. And this one, x plus 3 squared, all we need is that x minus 1, x minus 1, x minus 1. And we now see that each of these fractions has the same denominator, so we'll be able to combine those lickety-split, no problem. And then eventually, remember, we're just going to ignore the denominator, so why not start now? And we've got 3x squared plus 17x plus 12 equals a, and let's go ahead and FOIL this bad boy out, x plus 3 squared, it's going to be x squared plus 6x plus 9 plus b, I'll FOIL this one out, x squared plus 2x minus 3 plus c times x minus c. So multiplying c in there is pretty easy, so we just did it like that. Now we want to distribute everything through, so we get a x squared plus a 6x plus a 9 plus b x squared plus 2b x minus 3b plus cx minus c, and that all needs to equal 3x squared plus 17x plus 12. Now we want to combine all the like terms. So we're going to do this very strategically. We're going to put a squiggly line under every x squared. So we have an ax squared, we have a bx squared, and that's it. So we can say it is a plus b x squared. Now we want to find all of the normal x's, so we're going to do a dash line under anything that's a normal x. So that's a6 or 6ax. There's no x there. There's an x there, and there's an x there. So we've got 6a plus 2b plus c. So 6a plus 2b plus c x. And then we're going to go ahead and circle any constant. We've got an a9, we've got a minus 3b and a minus c. So let's switch it to 9a minus 3b minus c, and that's our constant. So we can now transform this into a system of equations. We've got a plus b x squareds. So a plus b needs to equal 3. 6a plus 2b plus c is the coefficient on x. So that 6a plus 2b plus c needs to equal 17. And this 9a minus 3b minus c needs to equal 12. So now we can go through and solve this. Let's go ahead with these two equations. We've got a plus c and a minus c. So if we just add these, we'll be able to cancel c out of there. So 6 plus 9 is 15a. 2b minus 3b, 2b or not 2b, in case you're studying English. 2b minus 3b is negative b, and c minus c is 0. So 15a minus b equals 17 plus 12, which is 29. Now we have 15a minus b equals 29. we can combine that with a plus b equals 3. So I'll go ahead and write a plus b equals 3 right there. We lucked out again. We've got a positive b and a negative b. If we add these together, b is gone. So we've got 16a is equal to, the b's are gone, 29 plus 3 is 32. A must equal 2. We just divided 16 over. So a is equal to 2. Now we can use the fact that a equals 2 to find b. If we plug it into this equation, we've got, so I'm going to replace a with 2 plus b equals 3. Subtract 2 from both sides, and we get that b equals 1. And now we know what a is, we know what b is. Let's plug it in to this equation to find c. So I'll do a wavy line. We've got 6 times 2 plus 2 times 1 plus c is equal to 17. 6 times 2 is 12, plus 2 plus c is 17. 12 plus 2 is 14, plus c equals 17. Subtract 14 from both sides, and we get c equals 3. How about that? Now, so let's go back to our original equality, and we're going to erase out the fractions that we multiplied them by to get common denominators. So this x plus 3 squared over x plus 3 squared, we're going to get that out of here. This x plus 3 times x plus 1, x plus 3 times x plus 1, and this x minus 1 over x minus 1 is gone. We're back to our original equality statement before we knew what a, b, and c were. A is 2, so this will be 2. B is 1, and c is 3. So we have successfully decomposed this monster of a fraction into these 3 parts. All right, I really feel like we're getting to know each other quite well. We're going to walk through another example here. Someone's walking down the street and they throw this fraction at you, expecting to stump you, but you know the first thing you need to do is factor this denominator, right? Right. So we know that it factors down to 2x squared plus 3 squared. Now if we were to FOIL this out, remember 3 squared would be our 9. We've got a 3 times 2x squared, so that's 6x squared, and there's going to be 2 of those that match up, so that's our 12x squared. And then 2x squared times 2x squared is 4x to the 4th. So with this factored, we can ignore it. And we know that there are 2 factors, but they're not unique. So that means we need to have this be the factor with ascending power all the way up to the power of 2. So this is going to be equal to ax plus b over 2x squared plus 3 plus not a anymore. Now we are on c x plus d over 2x squared plus 3 squared. And I guess I failed to justify why we did ax squared plus b and cx squared plus d. We do that because one of the rules said that if our factor is nonlinear, then the numerator on the other side will be 1 degree less. And it'll all work out in the end, I promise. So now, if we wanted to combine these to get a common denominator, the common denominator would be 2x squared plus 3 squared. So we only need 1 more of those for this one, and this one's already good. So let's go ahead and we're going to do that, and then we're going to multiply 2x squared plus 3. So essentially we just multiply 2x squared plus 3 on top and bottom here. The initial 1 got squared, now we have 1 on top. And now we have common denominators, and as we combine them, we're just going to ignore the denominators. So the next line we will write will be just the numerators. So plus 7x minus 6 is equal. Now we've got ax plus b times this, so I'm going to write that right here because we are going to need to FOIL that out, or term by term multiplication, however you call it. Ax times 2x squared, 2ax squared. Ax times 3, 3ax. B times 2x squared, 2b x squared. And b times 3, 3b. All plus cx plus d. Now we want to not multiply, but we want to match up the coefficients. So first let's, spot in there. Ax times 2x squared is ax cubed. Sorry about that. So we have a 2a x cubed there, and we have a 4x cubed there. So we know that 2a must equal 4, dividing each side by 2. A then equals 2. Now let's look at the coefficients on x. Here we've got a 3ax and a cx. Let me do something else. Just a hard underline. 3a plus cx, it's an x squared, equals 7x. I don't know why we skipped over x squared. There was no reason for that, but let's go and run with this now. So 3a plus c must equal 7. Therefore, we know what a equals already. So 3 times 2 plus c equals 7. 3 times 2 is 6 plus c equals 7. Subtract 6 from each side. C equals 1. Now let's go ahead and jump back and do x squared. We'll do underline, an under dash line. That's our only x squared here, and there's an x squared there. So 2b must equal -2, and divide each side by 2. B equals -1. Now we've got ABC, we need to find D, and so we look at the constant term. Let's go ahead and circle that. We've got a -6 there. We've got x cubed, x squared. Here's a constant, there's no x. Cx, and here's the other constant, there's no x. So 3b plus d needs to equal -6. We already found b to be -1, so 3 times -1 plus d equals -6. 3 times -1, -3, plus d equals -6. Add 3 to both sides. D then equals -3. So a is 2, b is -1, c is 1, d is -3. What we do now is we take these and we go plug them into our initial decomposition of ax plus b over all that good stuff. So remember, we multiplied this by a 2x squared plus 3 over 2x squared plus 3. So now we're going to get rid of that squared one, and we're going to get rid of the top. It's just like that. And we didn't multiply this by anything, so we're good there. But we want to replace a with 2. We want to replace b with -1, so we could just -1. c is a positive 1. So if we erase c and don't put anything, it's just like a 1x, but I'll go ahead and write it there, 1x. And d was negative 3. So this is going to be negative 3. And then our answer, remember it was that guy in the street we met that was trying to stump us. We can tell him confidently that this big fraction decomposes to 2x minus 1 over 2x squared plus 3 plus x minus 3 over 2x squared plus 3 quantity squared. So with partial fraction decomposition, there's a pretty neat little trick we can use to quicken our work. It doesn't work all the time, and that's why up until now we've solved all of them using a system of equations to find a, b, c, and whatnot. But this works sometimes, and like I said, it's really neat and it cuts our work down a lot. So we've already found the partial fraction decomposition of this earlier in the video, but we're going to do it again using the shortcut. So we know that this is equal, or we don't know, but we're going to set this equal to a over x minus 3 plus b over x plus 1. Remember that? So now we're going to do the same thing as we did before. We're going to combine these fractions, so we get a times x plus 1 over x minus 3 times x plus 1, and it's going to be plus b times x minus 3 over that same thing, right? And that's all set equal to x plus 9 over x minus 3 x plus 1. And since the denominators are the same, we're now going to ignore them, and we're going to say x plus 9 equals, and this is where it goes, it's a little different. We don't distribute this a through. We're going to keep it a x plus 1 plus b x minus 3. Now this is where it's different from what we did before. We're interested in finding a and b. So if we can pick a number for x that gets rid of b altogether, let's say if we got rid of b right there and we knew what x was, we could easily find a. What I mean is, in order to get this term to disappear, x needs to equal 3. So if we say x equals 3, everywhere we see the x, we're going to plug in that 3, so it's going to be 3 plus 9 equals a, 3 plus 1 plus b, 3 minus 3. Now 3 minus 3 is 0, and any number times 0 is 0. And so now we have 3 plus 9, which is 12, equals 3 plus 1 is 4, so 12 equals 4a. Divide each side by 4, and we get a equals 3. Now to find b, we want to do the same thing, but this time we want the a term to disappear. So last time we picked x equals 3, now let's pick x equals -1, because -1 plus 1 is 0. So plug -1 in for every x we see. -1 plus 9 equals a times -1 plus 1, so that's all 0, plus b, -1 minus 3, and I'm writing all wavy, I'm sorry, but -1 minus 3 is -4, so -4b is equal to -1 plus 9, that's 8, b equals -2. So when last time we used a system of equations, this time we picked values of x that'll cancel different terms so that we're left with just single equations with one unknown. In this case it was 12 equals 4a and 8 equals -4b. and then we take our a and our b and we plug them back in. A equals 3, b equals -2. I'm going to put the negative down here, so -2. And that's the answer we got before. So there's another way to do it, but it doesn't always work. So know how to do the system of equations as well. And finally, here's just a quick preview of calculus. We've already shown that this is true two different ways, one with using systems of equations at the end, and the other by picking strategic x values that cancel things out that we want. So in calculus, you'll do something what's called an integral. It looks like that. They're really cool. But if we wanted the integral of x plus 9, and now let's pretend this wasn't factored out, so that's going to be x squared plus, minus 2x minus 3. And then there's always a dx, which if you know what that is, great. If not, no worries, you'll learn it later. But if we wanted to take the integral of this is not very easy to find the integral of. But using partial fraction decomposition, we can decompose this fraction. So it becomes the integral of 3 over x minus 3 dx. We break it up into two different ones. Let's go plus the integral of -2 x plus 1 dx. And these two integrals, as you will learn in calculus, are recognized on site, and we're able to solve them very quickly with very little pain, no tears, whereas this one is kind of a monster. But partial fraction decomposition saves the day.